In this lecture, we are going to see about some important terms that we come across in the technique of FEA or finite element analysis. The first and most important thing is degrees of freedom. So how can we define these degrees of freedom? So the number of minimum parameters that are required to define the position or say state of an entity or an object inside space is known as degrees of freedom. So see here, if I have a point A here and then I need to specify its position in space. So let us take a 2D plane. So in order to specify the position of point A in this 2D plane, I need to define two coordinates, that are x coordinate as well as the y coordinate. So here we can say this particular point A has 2 degrees of freedom. Then coming to the same 2D plane, instead of a point we are going to take a line, and now we are going to define the position of this particular A. Now what I need to define the distance between this point and this line, and likewise I need to define the distance between these two entities, and then in order to completely define that position I also need to define an angle. So what happens is, here in this particular problem, in order to define the point A, we are going to define 2 translations and 1 rotation, which means for the point A we are going to have 3 degrees of freedom. Then coming to 3D space, if we take the same line, in order to specify the position A, I need to give 6 coordinates, total 3 translations and 3 rotations, which makes the total degrees of freedom for point A to be 6. Likewise, if you take for the point B also, it will be 6 degrees of freedom. Then DYF is very important concept. In FEA we use it for individual calculation points. So the total number of degrees of freedom for a given mesh is equal to the number of nodes multiplied by the number of degrees of freedom per node. So what happens is, the total number of equations that are going to be solved by the FEM problem depends on the number of degrees of freedom of the each node. So what happens if you have 6 nodes with 6 degrees of freedom? So the total number of equations to be solved by an FEA solver will be 6 into 6, that is equal to 36 equations. Then the number of degrees of freedom depend on the type of element. So if you take 1D elements, the number of degrees of freedom at each node differs to that of a 2D element and that of a 3D element. So for example, in a structural analysis, if you consider a thin shell, which is usually 2D element, it has 6 degrees of freedom for each node, in which you will have 3 translations and 3 rotations. While you take the thin shell element inside the thermal analysis, then the degrees of freedom will be only 1, that is the temperature degree of freedom. The degree of freedom of the total system, it depends upon the number of nodes and the type of element you have selected and the type of analysis you have selected. Then the most important concept inside FEM is the concept of meshing. So what do you mean by concept of meshing? So if you take a geometric body like this or solid body like this, in order to solve this particular problem, you need to convert this particular solid body into finite element body. The concept of converting a geometric model into finite element model, which contains number of discrete nodes and elements, is known as the concept of meshing. See, why do we need meshing? So if you take an original system in real world, what happens? Every system is a continuous system and it has infinite degrees of freedom. As I have told you earlier, if we have infinite degrees of freedom, then the equations to be solved in order to test the behavior of the system will be also infinite. Is it possible to solve that many number of equations? No. So that is why what we need to do is, we need to convert these continuous systems into a set of discrete systems, or say nodes and elements, in order to solve the problem easily. So for example, if we have converted, see here, we have converted this particular system into a system where it contains only 8 nodes and we have 6 degrees of freedom for 8 nodes, and so the total number of equations to be solved is 48. Likewise, see, coming to this particular example, if we take a circle here, then if we are going to try to include a triangle in this with the 3 sides, what happened? See, the area that is remaining, or the gap between this circumference and this particular line, is more. That means the error is also more. So once we take a complete system and we try to mesh it with a small number of nodes, what happens? The error will be more. Likewise, see, if I am going to go on increasing the number of sides of this particular polygon, and you see the distance or the gap between the circumference of this particular circle and this particular polygon is going to decrease. Likewise, what happens while we are going to increase the number of nodes and elements, we are going to get an accurate result. But this is not always true in every case, and we are going to see about this in the meshing part of our course. Then coming to the meshing elements, there are different types of elements. First of all, I am going to tell you what is a node and what is an element. So for example, if we take the 1D element, see here, these are the actual models. Say for example, if you have a truss or rod, or if you have beams, you can model them as 1D elements. So in the 1D element, see, these points are known as the nodes, and whatever the degrees of freedom are going to be defined, they are going to define this particular points, and the line which is used to join these two nodes is known as the element. So in order to model this type of problems, we are going to use the 1D element, meshing element, and we need to give the area of cross section for this 1D element as an input to the FEA software or FEA problem. Then coming to the 2D objects like say shell elements or plane stress elements or axisymmetric elements, we are going to take a 2D elements which consists of an area like this, and we need to provide the thickness for this particular area inside the any other FEA software which you are using, or otherwise if you are solving it manually, there also you need to provide the thickness. Then see here, these points are the nodes, and the lines joining these 2 points are nothing but the elements. Coming to the 3D elements, we are going to have the elements like this, and we need not give any additional input or additional requirement in order to solve this particular problems. Then coming to this elements, there are other miscellaneous elements that can represent springs, mass, rigid links, etc. In the next lecture, we are going to see how a finite element problem is going to be solved and what are the steps that are going to be followed to solve FEM problems in the industry. Thank you.